Hello, everyone. Thanks for joining us today. Safe and compliant electronic system design is a key topic across many industries where organizations need to conform to EMC regulations while reducing development costs and time. This is one of the reasons why the usage of simulation for EMC is growing to reduce design iterations and costly laboratory testing. My name is Jordi Soler from Altair's Global Business Development Team for Electromagnetics and Electronics. And today we'll show you how our simulation-driven solution is used to analyze and improve EMC, EMI at the board, subsystem, and system levels. That said, we'd like to start by introducing Altair in the context of electronics. First of all, we need to point out Altair's vision, which is the convergence between simulation, high-performance computing, and artificial intelligence, and how this can help customers to drive better decisions. And we are helping customers. In fact, we are helping more than 11,000 customers through a global organization of more than 3,000 people distributed across 86 offices in 25 countries, where Altair was founded in 1985. Today, we're a public company listed on the NASDAQ and with a revenue last year of 469 million. One of the markets where Altair continues growing and investing is electronics. In this market, you can see a projected compound annual growth rate of 7%, reaching 1.5 trillion in 5 years, and where in 9 years, the electronics in a vehicle could account for 50% of the value of a car. These are big facts, but they do not come without challenges. If we look at the automotive market, connectivity, e-mobility, autonomous driving, and shared mobility are four main trends, which come with more and more complex electronics, higher costs, and aggressive timelines in an environment with the standards to fulfill and with new regulations put in place. A bit more in detail in terms of challenges, we have higher speeds like with 5G or with automotive Ethernet, which can increase EMC, EMI problems, more wireless connectivity requiring more antennas, electronics reliability being essential in connection also with thermal, mechanical, and manufacturing aspects, among others. To properly approach these challenges, we need to talk about Altair's solution for electronic system design. We have been improving our solutions via internal developments and through strategic acquisitions to have today a strong portfolio used across organizations and by different types of engineers. Here, from left to right, we see solutions for PCB design review, analysis, verification, and manufacturing via PollEx. Then under electrical, we have wireless connectivity, EMC, EMI, and radar with FECO. Afterwards, we have our structural and thermal solutions. From there, you can see motor design, sensors, and actuators. We have system and circuit simulation via Activate. And last but not least, embedded software development, being many of these solutions HPC enabled and accessible on the cloud. Today, we'll go deeper into applications and use cases involving PollEx, FECO, and Activate, where it is important for you to know and keep in mind the fact that there is only one single license for the tools. In other words, you don't need to get separate and expensive modules. What you get and use are our units. You then have a pool of units. You draw units from the pool to access multiple products and across any location. The number of units you draw depend on the products you are using, on the number of simultaneous runs, and where you're running them. This solution is very flexible and scalable, while more cost-effective than other licensing systems where you need to purchase an additional license for each new product or module you would like to use. To conclude this first introductory section of our presentation today, we'd like to talk about basic and fundamental facts around EMC. We are basically talking about the capability of an equipment to operate properly in the presence of other equipment. while at the same time do not adversely interfere with other equipment nearby. On EMC, there is an emitter affecting a receiver through a coupling path, where such path can be either a conducted or a radiated mechanism. We can also either look at the emissions of a device or at its susceptibility or immunity to interferences. And which are two important factors which make EMC different from some other disciplines. Regulations and compliance. Standards are in place to ensure reliable and safety operation, and their compliance is mandatory. And it is not only this, EMC problems detected later in the development stage or later during the manufacturing phase can be really tricky to find and in some cases to fix. This is one of the reasons why it is extremely important to try to address EMC early in the development process. There are plenty of stories from where organizations have been learning and improving the way they design and approach EMC. Some of the elements in the powertrain of a hybrid vehicle can generate EMC, which can seriously affect and interfere with other systems in the vehicle. Cell phones can interfere with car keys. Radar interferences can seriously affect the performance and safety of onboard electronics equipment. And for instance, RFID tags can induce EMI problems into implantable medical devices. Now, how to approach EMC? We look at EMC problems from the board to system level. More in detail, there are cases where you may need to start by modeling and simulating the electronic circuit with Altair Activate, including our fast SPICE engine. Like, for example, in the case where you need to analyze the conducted emissions of the inverter part of the powertrain of an electric vehicle. There are cases where you deal with EMC problems where you need to include the PCB schematic and layout with Altair PollEx, paying a special attention to signal integrity, power integrity, and EMC aspects, including radiated emissions. And for these and other cases, you also need to include the field simulation via FECO to analyze, investigate, and define design guidelines related to radiated emissions at a component and/or at a platform level. If we focus on EMC at board level, here is where PollEx comes into play. Being a PCB Signoff solution used by multiple and major global electronics organizations like Samsung, LG, Hyundai Motor Company, or Qualcomm, to name a few. First of all, it is an open ECAD environment. No matter the ECAD you are using, you can directly import into PollEx your PCB designs created with the most common tools from Altium, Zuken, Mentor, Cadence, and others. And you work with a single interface with the same database solution used across your organization, not only by the EMC and electrical engineers, but by the other engineers who also need to review the designs and work on verification and simulation of PCBs. Here, I would like to now touch on PCB verification, usually known as DFX. Board verification brings post-design into early design stages, which is especially useful to significantly reduce the number of design iterations. Such verification is done through a set of rule-based fast checking tools, which detect design faults which can cause electric failures. We call this DFE, or faults which can occur during manufacturing, DFM, or during the assembly process, DFA. When is verification used? Here you can see a basic electronics development and manufacturing process from logic design to assembly. Electrical verification is done at a schematic level before doing the placement, and DFX is more and more used when the layout is available and even before doing any simulation. If we focus on electrical verification, we are here talking about automatically and quickly detecting and eliminating electrical defects related to SI, PAI, EMI, and ESD in early design stages. There is a solution to check electrical validity at the schematic level, and another one focused on the layout, where a wide set of geometrical checking rules used by many global electronics companies are used. The rules are classified by groups depending on whether they relate to high-speed signals, differential pair nets, and if they are related to the board, power, or components. And on top of this, you can also do advanced verification, combining rule checking with simulation, where the checks are not done with geometrical values, but with simulated electric values. Here you are some examples. Currents flowing on a signal trace have a return loop, where the current comes back to the source through the return path. Such path depends on the frequency. For low frequencies, currents follow the path with least resistance, whereas at high frequencies, they follow the path of least inductance. To reduce the length of the return path, you want the signal trace properly shielded by a solid ground plane below or by a coplanar ground. However, any discontinuities along the shortest return path make the current to go around such discontinuities, and at higher frequencies, this can increase EMI. PollEx can find all these cases on a layout design, so they can be analyzed and fixed. There are other cases where you need to check if the shielding on particular traces and nets is enough, or to introduce ground vias near an EMI source on the board, or to properly place coupling capacitors to ensure a stable power supply. One example of leading organization using PCB verification for electrical as well as for manufacturing is Samsung SDI, a top player as an energy and materials provider of rechargeable batteries for IT, automotive, and energy storage systems. I'm not going to go into the details, but I recommend you read this story and also watch a video interview you can find on the link shown here at the bottom. That said, now I would like to jump from electric board verification into a story related to EMC shielding, another important application covering board and subsystem simulation. To go through this application, we have selected a story from Hyundai Mobis, where they have been able to improve the process for shielding effectiveness via EMC simulation. A bit more in detail, the case is focused on the around view monitor, a system used to assist drivers to park more efficiently. Such system includes a PCB and a housing. They imported into FECO the simulated near fields of the PCB. With such imported simulated data, FECO creates an equivalent source. Then they included in FECO the model of the housing, and they simulated the currents and near fields caused by the radiation of the PCB on and around the housing. With this approach, they could see the areas where the currents were higher, hotspots, and by adjusting the slots and connectors, such spots were reduced and even eliminated, which permitted them to increase the shielding effectiveness of the housing and hence reduce the level of radiated emissions. Also, they did several tests with FECO to analyze the effect of using different materials for the housing on the shielding effectiveness. On the graph, on the image on the right, part of the full story you have on the link below, you have simulated results of the shielding effectiveness of our frequency for 5 different materials that were considered. And now, after having seen the Hyundai Mobis story, we'd like to show you the new solution and workflow to address radiated emissions of a PCB combining Altair PollEx with FECO. We basically start with PollEx, where you simulate in PollEx the currents on the board and where you export such currents into a file that you afterwards import into FECO. Once in FECO, you convert such currents to an equivalent source, which is used to analyze the radiated emissions from the board alone, integrated in a system, or being part of a test setup at a component or platform level. Let's now look into a concrete design case. Here you can see the layout of a 6-layer PCB of a multimedia device using a CPU driving signal into 2 DDR3 memories. We focus on 6 major interfaces, HDMI 1.3, working at 3.4 gigabits per second, a frequency of 1.7 gigahertz and 4 pairs of unidirectional differential pair nets. USB 2.0 at 480 megabits per second, a frequency of 240 megahertz, and with a bidirectional differential pair net. and DDR3 being the data strop and clock signals differentials, and the data and address line single-ended, with 1000 megabits per second and a frequency of 500 megahertz for all of them, except for the address line running at 250 megahertz. From here, we select the 6 nets representing each interface, and we set up the model with the pulse period and using the related IBIS models, including the proper driver strengths and receivers. From here, you run the time domain analysis to calculate the currents on the board. The waveform results can be visualized in the time and frequency domains. And here you can see the frequency domain current waveforms related to the 6 nets to analyze the basic harmonics from such interfaces. By looking at the peaks, we can identify the DDR3 address in yellow and clock in green lines as the major contributors to EMI. Reason why, in this case, we now focus on these 2 lines. Then we select these 2 problematic nets, which you can also see on the right in PollEx at the top with the 3D net and the standard layout views, and at the bottom with the net topology viewer. Once selected, we repeat the analysis where we calculate and export the currents due to those nets on the PCB into what we call the .rail file, radiated emissions interface file, to be afterwards imported into FECO. So now we move from PollEx to FECO, where we import the rail file, and which includes the currents on the board for the selected and problematic nets, and we create a PCB equivalent source with the desired frequency band. From here, we calculate the radiated near fields from the PCB at a distance of 3 meters on the horizontal plane. In this case, as we are considering the requirements in HIRF 32 standard on electromagnetic emissions for multimedia equipment. Once we have run the FECO simulation, we can now look here at the near fields at 3 meters against frequency and for 4 different angles where you can see the frequencies of the peaks, starting with 250 megahertz, frequency of the address line, 500 megahertz related to the clock line and their related harmonics together with their amplitudes. And on the right, you can see the near field pattern on the horizontal plane at 250 megahertz to get more insights around the directions where radiated emissions are higher. Now, and as I was mentioning when I was introducing this particular case, we want to add a shielding enclosure to reduce the radiated emissions from the board. A bit more in detail to illustrate the process, we put the PCB source inside the shielding enclosure, as you can see on the right. We'll simulate the radiated emissions also at 3 meters, and we'll analyze different possible materials for the enclosure. You can now look at the radiated fields at 3 meters, on the left at 250 megahertz and on the right at 1 gigahertz. The results without shielding enclosure are in dark blue, whereas the other results are related to 3 concrete possible materials. If you look at the conductivities of these materials and at the radiated fields, you can see, as expected, how the material with higher conductivity provides more shielding. However, in a practical design, other aspects need to be considered besides shielding effectiveness, like cost and manufacturability. Also, in some cases, and depending on your particular problem, you may need and want to simulate the EMC test setup at the component or platform level. Here on the left, we are showing the simulation in FECO of the test setup at the component level according to HIRF 32, including the semi-anechoic chamber, table with the strips connected to ground, the PCB source, and the receiving antenna. On the right, you can see radiated emissions at 250 megahertz in the horizontal plane, with the PCB source alone in red and with the test setup in blue, where you can see the increased field levels when including the real test setup. That said, a recommendation is to start with only the PCB source to get quicker results, and afterwards, if and when necessary, consider adding the test setup in the simulation. When considering the coupling between PollEx and FECO for board radiated emissions, we have today another example from a well-known consumer electronics company that we would like to explain to you. This is a case where we have a board with a MCU, an HDMI interface connected to an HDMI cable which at the other end is connected to a display. The request here is to analyze potential radiated emissions coming from the cable. A bit more in detail, if we look at the HDMI pinout, we have 3 data lanes and 1 clock lane. The data rate per data lane is 1.65 gigabits per second, a frequency of 825 megahertz, and the clock frequency is 165 megahertz. Also, each lane consists of a differential signal with 2 pins for plus and minus, and 1 pin for the shield. Which is the approach here and the simulation workflow? There are 3 main steps. First of all, you need to model and calculate in FECO, which is the input impedance of the HDMI cable. The second step is to model the board in PollEx with the HDMI port loaded with the cable impedance previously calculated, and then run the simulation to get the waveform exciting the cable. Finally, you go to FECO and simulate the radiation of the cable being excited with the waveform calculated in the previous step with PollEx. This is the model in FECO, where at the top left you can see the HDMI cable cross-section. And here on the right, you have a 3D cylindrical scan of the radiated near fields around the cable, very useful to more quickly see where is the maximum. You can also see the near fields against frequency with the peak amplitudes at expected frequencies, including 825 megahertz related to the data lines. Now let's jump into another customer case, now from an automotive OEM. Here the issue was an interference from a wiper motor being coupled through a cable to a control unit, causing a false triggering of a sensor. A bit more in detail, on the left, you can see the wiper motor connected to a relay box through a cable shown in blue. Also, you can see a control unit connected to a pressure sensor through a cable shown in purple. On the right, you can see that the wiper motor cable consists of a power line and a ground line, whereas the other cable has 3 wires: power, ground, and also signal line. The noise signal at the wiper motor cable was measured, and this was the excitation. Then the received noise signal at the sensor was both measured and simulated, where the customer could see the expected agreement between them. From here, the issue was that the threshold level for the pressure sensor was 0.5 volts, and the interference coming from the wiper motor cable was generating a peak above this threshold, triggering a false event. One of the approaches this OEM followed to fix this problem was to analyze possibilities to use other types of cables. In this case, they switched from a non-twisted pair to a twisted pair, where thanks to it, they could reduce the level of interference to a value far beyond the sensor threshold level. We have been talking about radiated emissions, and now we'd like to show you one example related to radiated immunity, which is also key for applications like safety systems and autonomous cars. Here, FECO is used for the simulation of the automotive immunity test according to ISO 11451-2 substitution method for Peugeot 508, the sedan variant with 5 doors and the roof fully metallic. This is a schematic of the test setup, considering the right dimensions and distances as defined by the standard and including the transmitting antenna. We have a complete presentation we can show you, but today, for the sake of time, here there is a comparison between measurements and FECO simulations for one of the considered positions, P10, when considering the transmitting antenna placed in front of the vehicle. On the top right, you have the results for the horizontal polarization, and for the vertical polarization, you have the results on the bottom right. The comparative study between simulations and measurements shows a nice agreement up to 450 megahertz, And for higher frequencies, there are some differences between simulation measurements caused by the effect of non-metallic parts of the structure that are not included in the simulation model. Having seen this, we have two more customer cases to show you today. The next one is related to electrification, and in particular to the emissions of the high voltage system of an electric vehicle. You can see the battery connected to the inverter through the DC cables and the AC cables connecting the inverter to the electric motor. The goal here was to calculate which was the noise radiated from the cables being coupled into the windscreen antenna, as such noise can cause interference and degrade the performance of radio reception. In terms of some of the results, you can see here the received noise signal against frequency at the AM antenna port, noise coming from the radiation of the cables. This is from an OEM with a strong strategy and plan to massively reduce measurements and testing and to increase simulation, going from the hardware to the digital prototype. If we continue looking at the powertrain of an electric vehicle, we indeed need to consider both conducted and radiated emissions. This is a case from a major automotive OEM and a tier 1 supplier we work with. For conducted emissions and related to the inverter, we use circuit simulation to model the related test setup according to HIRF 25. We will afterwards also leverage such circuit model and results to work on the radiated emission tests at both component and vehicle level. Here you can see the circuit in Altair Activate with the elements of the test setup: battery, listen, inverter, DC and AC cables, and electric motor. Each one of the blocks contains the related equivalent circuit model, and in the case of the cables, the S parameters for them. The circuit simulation engine is PollEx SPICE, our fast and accurate SPICE solver. As defined by HIRF 25 standard, we are simulating the common and differential mode voltages at the output of the listen. And this is what you can see on the right, where we would like to point out two aspects. One is the expected higher amplitudes for the common mode voltage, and the second one is related to the frequencies of the peaks, as they are directly related to the switching frequency of the inverter, 34 kilohertz and intermonics. This modeling is not only interesting to analyze a particular design, but also to assess possible changes and improvements to create design guidelines. If we now move to the simulation of the test setup for radiated emissions at the component level, here on the left you have an image from the test setup defined in HIRF 25 standard, and on the right you have an image showing the model in FECO reproducing the real test setup. Although the model in terms of elements is self-explanatory, it is worth mentioning here that in this model, the cable N connected to the inverter is excited with the output signal of the inverter previously calculated with the circuit simulation. And also the equivalent models for the battery, inverter, and motor are included. For the results, we need to simulate and analyze the voltage at the antenna port, antenna capturing the radiated emissions from the inverter as part of the defined setup. In dark, you have the mask, the maximum permitted values. In gray, you have the spectrum given by FECO, and in blue, you have also the spectrum simulated by FECO, but after being post-processed, so it shows the spectrum format that you could get by doing the measurement with a HIRF 16 EMI receiver. Therefore, you are indeed simulating what you could measure, and where in this case, you see 3 peaks and frequencies going above the limits. We extend this case by now addressing the analysis at a platform level with the vehicle in this case. Basically, we have taken the setup and mounted it in and on the vehicle. This is important for the OEM, but also for the tier 1 supplier in those cases where the OEM is asking them to validate and demonstrate the performance of the component or system once installed in the vehicle. In this graph, you have the received signal by the monopole on the roof in green, which you can easily compare to the results only with the setup at the component level in blue. But not only this, there is another important typical situation. Components are tested with a standard length of cable, but once installed in the vehicle, the length of the cables connected to such components can change significantly. For example, we slightly increase the length of the AC cable on the vehicle. Such results are in red, and you can see the differences with the original length in green. And we will finalize today by showing another example, but in this case related to aerospace from one of our existing customers. It is about HIRF with a signal illuminating part of an aircraft where inside there is a 9.6 meter long cable bundle. The goal is to analyze the induced currents within the cable and at its terminals from 10 kilohertz to 200 megahertz. The cable bundle has 3 twisted pairs, 2 shielded, 1 unshielded, all of them inside a double shielded bundle. And here at the bottom, you have the cable schematic showing the connectors and connections and elements across the different pins. In terms of results, today we'd like to point out the type of results the customer was looking for. On the left, you can see induced currents at some of the connector terminations. And on the right, you have the sum of the currents from concrete and selected signals within the cable. And this is all what we wanted to show to you today, where by using several examples and customer cases, we have explained to you how to leverage EMC simulation covering from board to system level. Based on your current and future needs and challenges, you may need to go through the whole process or start with a part of the solution.